In class today, you saw a number of examples that used different strategies for solving exponential and logarithmic equations. So this video is going to show a couple of more particular equations that would have you approach them somewhat differently than the way we had approached solving the equations in the first few examples. So let's consider this supplementary problem where we have the log of x to the base 8 plus the log of quantity x minus 12 also to the same base being equal to 2. Okay. So as we begin our solution, what I would like you to take note of is the fact that we are adding two logarithmic expressions together that have the same base. So again, we're adding together two expressions that have the same base. So recall that this does allow us to combine those expressions as a single logarithm to the base 8. So you might want to indicate that that was due to a particular property. That is the product property or the product law. So the log of xy to the base a was equal to the log of x to the base a plus log of y to the base a. Okay, so the product law. Now that we have it in this form, what I would ask you to consider is the following. Okay, let's just say that quantity x onto or multiplied by x minus 12 was nothing more than some other expression. In fact, let's say it was the log of some other variable. Call it m. Okay, call it what you like, was equal to 2. Okay. What we would then do with that expression in order to solve would be to represent it as an exponential equation. So we would then take our base of our logarithm, express that to the power of 2, which would give us a value for m. Okay? So that would all come into effect by letting m be equal to x onto x minus 12. Okay? So by making that substitution, by converting to exponential form, and let's just put that in here. Okay, also, just for you to recall, we'll bring this out here. This sort of describes, right, the difference between going from value to base to the exponent, and then from the exponent as being equal to the log of the value to a particular base. With this information in hand, okay, we can now go back and experience this problem without necessarily having to do the substitution. Okay, so what I mean by that, and you can absolutely keep this methodology the way that it is, okay, absolutely positively. There's actually nothing wrong with continuing as such. In fact, we could go further, say that 64 is equal to m, look back at our solution to see what m is set equal to, which is in fact this. So we have 64 is equal to x onto x minus 12. Going a step further, now we have a quadratic equation. So we can connect this back to an earlier part of the course. Okay, where 64 is equal to x squared minus 12x, setting one side to 0, and moving forward with this, we end up with that quadratic equation. The alternative that I was talking about, that is the bypass, if you will. Let's just remove this material for now, and we'll split our screen out so that we can write it this way. So if we were to take this information here and we were to apply a pair of scissors and cut this away, what would we see in the middle? Okay, we would specifically see the following. Taking this form and rewriting it as 8 to the power of 2 equals x onto x minus 12. Okay, and hence 64 equals x onto x minus 12. So very quickly, without the substitution and recognizing how to convert from logarithmic to exponential form, we can get ourselves here very quickly. So let's go ahead and continue solving this particular equation. So what we need to do is to determine the type of roots that we have. Okay, so let's look at real versus non-real roots. Okay, by determining the discriminant. So b squared minus 4ac is going to be minus 12 squared minus 4 by a by c. And as you can see, we are going to end up with a positive value. Okay, so we'll have 144 plus 4 times 64, which should be 256. Okay, so just double check that we've got that right. We'll add these together. So let's see, 6 and 4 make the 10, carry the 1, another 10, and it looks like we have 400. Okay, so while we're at it, we do have to solve for the value of x. So why don't we get this ready for the quadratic formula. So we need the root of 400, which is the root of 4 times 100. And of course, we can see that as being the root of 4 by the root of 100, or nothing more than 2 times 10. So we know that the square root of 400 is 20. So using the quadratic formula, we can determine the values of x. Recall that's negative b plus or minus the root of b squared minus 4ac all over 2a. We've already done the work to figure out the square root of the discriminant. That plus or minus piece is 20. The 2a is 2. And the negative of b, if we go back and look at our b value, right? The b value is minus 12. We take the negative of minus 12 and we have 12. So what that means is that x is going to be 12 plus 20, or 32 over 2, which is 16. Okay. Or 12 minus 20, which is negative 8 over 2 minus 4. Okay. So last but not least, we want to check to see if the expressions in the equation are defined. That is to say, if I substitute these values of x back into the equation expressions, will they be defined? So, if we consider the log of x to the base 8, okay, if we were to substitute these values in, we know that it is defined for all values of x that happen to be positive. n greater than 0. Okay, so we can't take the log of a negative value, and of course we can't take the log of 0, because there is no particular power that produces 0 as an answer. So if we look at the values we have, that implies, right, that x equals 16 is admissible, but x equals minus 4 is not, so inadmissible. Okay, or in other words, i.e., we could say that the log of minus 4 to the base 8 is undefined. Now, I won't write it in this example, but by the same token, if you go back and write about this expression here, okay, you would find that for one of the values, that expression is defined, and for the other one, it is not. Okay? And in fact, it is for the same value. 16 is defined, but x equals minus 4 will not. Okay? So you would add one more line, one more sentence underneath that, and then restate your solutions, and you've got a perfect solution to this problem. Let's check our running time on this. We'll try to keep this down to about less than 20 minutes. So let's go with one more. Let's try this one here. Okay. You will see some of these problems come up within your textbook, and it's as opposed to being a logarithmic equation, we now have an exponential equation. Okay. What I'm going to do is I'm just going to write down a couple of things. You can hold off on doing this because I want my words to be visualized. So what I want you to think about is this. If you and I had either one of these equations, we would have, hands down, a strategy for solving these. We would take the common log of both sides, or maybe use the base 10 log, and use our laws in order to determine the value of x. But the situation becomes complicated, or another strategy is required when we are trying to add or subtract exponential equations of the same, exponential expressions of the same variable. So what I would have you consider is this. Think of the expression 10 to the x. What I would want you to do is to think about, how could I get from 10 to the x to 10 to the x plus 1? How do I manipulate this expression using my knowledge of exponents to arrive at a plus 1? Well, in order to add exponents, the bases must be the same, yes? So if we have 10 to the x, and I expect to add 1, then I must multiply that by 10, or 10 to the 1. This would get me to 10 to the x plus 1. So what this means is that if I go this way, I'm breaking that power down. I'm factoring. So factoring becomes a strategy for us to manipulate this equation that we can work with it. So if we were to rewrite the first expression as such, I'll leave the second one alone. Have a look to see what is common between the expressions. We have 10 to the x, 10 to the x. So it would make sense to common factor. So let's do some common factoring. Let's pull out 10 to the x, and we're left with 10 minus 1. Okay, you can see that here, the 10, of course, that's 10 being here, and the minus 1, of course, is going to come out of this term when we divide it by 10 to the x. So we now have this equal to 9,000. If we tidy things up a little bit, we'll have 10 to the x multiplied by 9. That equals 9,000. Let's cut out one of these factors. We can divide out the 9. That cancels. This is the lowest form of 1 over 1. And we have 10 to the x equals 9, equals 1,000. Okay. Not much more is left to do here other than to write our answer for x. And as you can see, just by eyeballing this, 10 cubed is 1,000, and therefore x is equal to 3. Checking the value of our root as x equals 3, we know that whether the exponents are positive or negative, it will have no effect on the admissibility of those roots. So x equals 3 is an excellent answer.